we'll be defining what an inner product is, and we'll see the first example that's not Rn with the regular dot product. All right, so I'm going to start with any vector space. I'm going to ask that I have a product, so an inner product on V is a map. So we'll denote it as these triangle brackets are quite common, so I'll use them. That means I have to be careful. I won't use them anymore for vectors. I'll use the square vertical vectors, just because otherwise I feel like it's a bit confusing. It should be clear, but not enough to use it. So here, it's going to take two elements of V and give me an element of R. So if I apply it to V and W and V, I should get an element of R. All right, so I'm going to have a bunch of different properties so that first thing I want is that VW and WV give me the same product. So for all VW and V, VW and WV are the same. All right, and then I need this product to respect the vector space operations. So for all V in V and K in R, V, let's put W as well. So if I take KVW, that's going to be KVW. So I'll be able to factor the real number out and multiply the product without the K by K afterwards. All right, the other operation of vector space is the addition. So for all UVW in V, U plus VW is UW plus VW. All right, so notice I only use the operation on the first of the two elements, but because of the property that I could switch them, that means they're also true on the second. So I could distribute the product on the sum in W's, and I could take out a constant in front of W here as well. It would just mean using property 1 twice as well, but we'll just see that it works. All right, and then last, because I want to use this product to get lengths, I'd rather make sure that if I take VV, so the product of V with itself, this needs to be bigger or equal to 0. And then more than that, I don't want it to be 0 unless V itself is the 0 element. So if VV is 0, that means that V is the 0 element. Alright, so these 4 properties seem like a reasonable thing to ask for. The product that you're defining on the vector space needs to respect the vector space operations, and it needs to give a good length, so we need property 4. Alright, so let's look at a couple of examples. Example 1, I'll put it right here. If I use the dot product on Rn, that's going to give me, I forgot part B. If I have a vector space with an inner product, that's going to be called an inner product space. All right, so I have an inner product. And if I look at V, once it has an inner product specified, it's going to be called an inner product space. All right, so let me look at an example. The first one is going to be pretty short. We're just going to look at V equals Rn, and VW is V the W. All right, so the example that we started from, the dot product, is an inner product. And so Rn, the Euclidean space that we've been working with, is an inner product space. If that's the only one we have, we wasted 10 minutes of our lives, but of course it isn't. Let's take one of these, so take V equals R2, and I'm going to define a new inner product in R2 that's just slightly different from the one we had typically. So for VW in R2, I'm going to define this will be 1/9 of the first component multiplied, V1 W1, plus, let me make sure I use the right number, 1/4 V2. So it's just slightly different than the regular dot product. I introduced this weighing constants here that change a tiny bit what I'm going to get. Let's prove that this does indeed give us an inner product. So I'm going to need to prove the third property. First property, I can switch the order of V and W, will not affect my answer. So if I start with WV, that's going to be 1/9 W1 V1 plus 1/4 W2 V2. Of course, now at this point, these are real numbers, and I know I can switch the order. So I'll get 1/9 V1 W1 plus 1/4 V2 W2, which is VW. All right, so first condition is true. Second, I want to make sure I can take constants out of the dot product. So I want to look at KVW. The components of KV are going to be KV1, KV2. So I'm going to get KV1 W1 plus KV2 W2. Again, all numbers here, KV1, V2, W1 are all real numbers, so I can just factor K out of everything. And so I do get K times VW. Third property, I have to look at addition. So I'm going to look at u plus v w. And let me use u1, u2 for u. So this one will be u1 plus v1, u2 plus v2. And so I will get, let me get a better one, this one's running out. I'm going to get 1 over 9 u1 plus v1 w1 plus 1 over 4 u2 plus v2 w2. Now these are real numbers, so I can expand, I can distribute the w1 in. I will get 1 over 9 u1 w1 plus 1 over 9 v1 w1 plus 1 over 4 u2 w2 plus 1 over 4 v2 w2. And now if I look at these two terms together, I'm going to get the product of u and w. So this part here is the product of u and w, while the right terms give you a product of v and w. I have one more property to prove. I need to look at what happens when I plug v twice. So I need to prove that it's usually positive and it's 0 exactly when the vector is 0. So here, if I look at VV, I'm going to get 1/9 V1 V1 plus 1/4 W1 W1. And so I get 1/9 V1 squared plus 1/4 W1 squared. That's going to be positive, this will be positive, so this is definitely positive or equal to 0. The second part of property 4 looks at when this is exactly 0. So let's look at that. So VV is equal to 0. If and only if this is 0, which is going to be true, well, as soon as one of them is bigger than 0, the other one's positive, so I'm going to be bigger than 0, so we need both of these to be 0. So V1 is 0, and W1 is 0, and that's the same thing as saying that V is the 0 vector. We proved the 4 properties, so we have an inner product.